Good evening, everyone. I am Seung-Bin Kwon, Chair of Quantum and Introductory Seminar Manager of QISCA. It is my pleasure to introduce today's introductory seminar presenter, Sawon Choi from QIA. Sawon Choi is a junior undergraduate student in the Department of Physics at Yonsei University, currently conducting research in Professor Chaeyeon Park's lab. Their work focuses on quantum error correction, quantum error migration, and variational quantum eigensolver algorithms implemented on IBM's real quantum hardware. Driven by a deep interest in the convergence of quantum algorithms and machine learning, he has organized this introductory seminar on quantum machine learning. Today, he'll be presenting a talk titled Introduction to Quantum Machine Learning, sharing insights from the paper, A Quick Introduction to Quantum Machine Learning for Non-Practitioners by Ethan Evans and others, Introduction to Quantum Machine Learning and Quantum Architecture Search by Samuel Chen and Xing Liang. Please join me in welcoming Sawon to the stage.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay, hello, everyone. My name is Sawon Choi and Vice President of KIA. Today, I talk about quantum machine learning, QML. QML is a part of a larger topic called variational quantum algorithm, or VQAs. In this seminar, I'll explain the key ideas and how these algorithms work. Okay, here's today's outline, and we are going to talk about machine learning and quantum machine learning and data encoding, quantum neural networks. Okay, machine learning is like finding pattern recognition in data and make prediction even without directly told what to do to machine. There are four main types, and one is supervised learning, and one is unsupervised learning, and one is reinforced learning, and one is deep learning. Like as you can see from the diagram, the left side of my slide, you can see the artificial intelligence is a big main thing, and the following is the machine learning and deep learning. Most of you guys have heard of what machine learning is, but we are going to talk about how deep learning works first and understanding how quantum machine learning works later. Deep learning is based on something called neural networks, like artificial conducting mathematical based neural networks, and it works very well for hard tasks like recognizing images or speech and understanding language, just like ChatGPT, like you know. And you can learn directly from the dataset and make accurate predictions. But why quantum machine learning at this page? As machine learning gets smarter, it also needs more data to train on. A good example is ChatGPT, like I said. It's a huge model with billions of settings. Parameter training takes a lot of data and computer powers, meaning it consumes a lot of energy, for the example, electricity. So at this point, classical computers can handle this, but as the data grows and goes more complex, large number of data sets, we start to hit limits on speed and resources. For really large tasks, like recommending videos to billions of YouTube users, classical computers could make a recommendation for each of users. But it could be kind of slow, and of course, it consumes a great deal of energy too. So we begin to ask that can quantum computing can help more machine learning faster and better? This is what QML is trying to do. This is just simple page of how quantum machine learning is consisted of, and the biggest one is quantum computing, and the second thing is variational algorithms called VQA, and uh, and inside that is quantum machine learning. This means QLM is type of VQA, which is special kind of algorithm that use both classical and quantum computers. So these are very useful in today's noisy intermediate scale quantum areas computers, machine learning that still have some noise and are not perfect. On the right side, I'm going to explain how VQA works. At first, VQA works by encoding the circuit with classical data or something data we want to train up. And we are going to apply variation of quantum circuit, which is consists of parameterized theta value, as you can see over there. And we are going to measure this quantum state, and we are going to update parameters from measurement. This is how VQA works, and quantum machine learning has the same process like this. Okay, so like I said, variational quantum algorithm is consists of data encoding and making quantum circuit and measurements and parameter updating. We are going to explain how data encoding works first. In QML, data comes in two types, classical and quantum. Classical data includes things like binary numbers, like like 0101, and things like text or just classical images. And quantum data is stored in qubits and behaves like unknown data. Like we don't know how exactly the data is stored, and it's consisted of like proportional probabilistic data. So to use classical data on quantum computer, we need to encode in a quantum way, and there are lots of methods to encode it in a quantum way. So these are the following methods to encode in quantum way. One is basis encoding, and this is like mapping binary data directly to 0 ket and 1 ket, each respectively. As you can see the slide over there, just number 3 data is converted to binary data, 1 1, as you can see the binary information, and 1 1 data goes to 1 1 ket data. And following like 1 data goes 0 1 and it goes to 0 1 ket. This is how basis encoding works. And as you can see, the data has a like capacity of n qubits to like we need to transform into binary information, and we are going to transfer to that to quantum. And this kind of looked like inefficient, so we designed a method called amplitude encoding. Amplitude encoding is like encoding data to amplitude, and which means the weight, which can be considered as a weight of like parameterized vectors over there. You can see if we want to encode the data such like 3103, we are going to transform that to normalized amplitude. And you can see there like summation of 3 squared plus 1 squared plus 0 squared plus 0 squared. You can see the data is transferred like that. And the last one is angle encoding. Like, if you imagine the how below sphere works in quantum way, we are going to like map data into rotational version of how vectors propagate. So we are going to map data into rotational angle of qubit, and this is kind of similar to amplitude encoding if we regard this in Z measurement. Okay, and we are going to explain how machine learning works first. And then we are going to explain how quantum machine learning. The basic concept of machine learning is like gradient descent, which is calculating a gradient of loss function with respect to parameters. And we are going to update the parameter to the direction of minimizing loss function. Loss function is kind of like we want to minimize the function of the losses. For example, loss function is mainly used like mean squared error function. And as you can see the graph over there, we have a large number of data sets, and we are going to find the minimal value so that we could get the minimal result by using gradient. And there are lots of kinds of methods using this gradient, and one of them is batch gradient descendant, and it's kind of aggregating the updates of parameterized value set to for all training examples. Similarly, VQA used a similar process. Variational quantum algorithm, like I discussed earlier, from quantum mechanics is inspired by variational method. What is variational method? Variational method is called like minimizing the expectation value of Hamiltonian is larger than the lambda minimum to like we could guess. In a like quantum chemistry, the minimum value can be considered as zero ground state energy of this function. And we are going to find the algorithms to find how this expectation value of Hamiltonian works. In order to achieve this, we are going to introduce the parameter shift loop. It's basically kind of like it's hard to get gradient directly from quantum circuit. So using two changes on parameter to calculate gradient. This can achieved by like having unipotential operation to exponential I theta, parameterized theta, G, and G is of course the like Hermitian operator. And we are going to change unitary operation to like some mathematical calculation, and we can get gradient from this directly without having actual gradient like differential method. We are going to get gradient from just subtracting from one to other thing. And these are like the derivation is an exact derivation. And since this is like introduction seminar, we are not going to discuss all the details closely. But if you want to see that this is known from various papers, and as you can see, the like expectation value of Hamiltonian is considered of like loss function, and we are going to find the method to extract gradient from that. Yeah, this is the same page. So why this is surprising? This is surprising because we are going to use gradient to optimize in QML. Like among QML, there's quantum neural network we are going to discuss. And yeah, this is what I want to know from the gradient. From theoretical background, from classical neural network. And classical neural network is like making artificial neural, mathematical neural network from having input and hidden and output layer, just like the neurons in our brain cells. Neurons in our brain cells get from data, and we process data and we give data to other neuron cells. So this is kind of very similar page on the neural network. And we are going to use the perceptron and nonlinear activation function to make this mathematical approach work. And through backpropagation and gradient descent methods we are going to update rates, which means we are going to learn from getting gradient, and we're going to use gradients too. So what I said from earlier methods, we are going to use parameter shift rule to extract gradient from the quantum circuit, and we are going to use that in like just like classical neural network. So we are going to extend the functionality of traditional perceptron using quantum principles. And this operation in quantum form includes input data in qubit form, obviously, because we are going to use this in a quantum circuit. So this is kind of similar to multiplying and adding weights in traditional perceptron, like what I said, learning. And quantum perceptron process multiple inputs and simultaneously through qubits, which is possible because it has like superposition technique, and we are going to calculate it at the once. We got unlike to quantum machine learning, unlike to classical machine learning, could handle this by just one by one. Okay, this is what quantum neural networks, and this is kind of different from conventional neural networks because there are models that multiple data re-uploading is possible. Multiple data re-uploading is like I'm gonna discuss later on after this slide, but it's a method that can upload data repeatedly to another quantum gate. And it has a characteristic called universal quantum classifier. If you get the help of tracing method, even in a single qubit, QNN can approximate functions in a single qubit like using universal quantum classifier. And multiple data re-uploading is allowing the multiple re-uploads of given data to the circuit to allow more complex characteristics. Well, complex functions or patterns can be approximated by data re-uploading and QNN. This process of repeatedly inputting the data into the circuit, this enables conversion in a way that reflects Fourier coefficients. As you can see from equations, they are like there's weights are summated, weights are aggregated from the summation, and each first uploading is like we can consider this as like encoding the first data to a circuit, and we are going to get the learning process from in quantum circuit. And while the learning is processed like having quantum circuit and measuring and updating parameters, this is called like learning process. And while learning circuit, we could add the some frequency components like to uh, like just adjusting the parameters, and each entered could be entered to quantum circuits during data re-uploading, and it can be thought as discrete Fourier series, and it can be seen as optimization process of machine learning, like while the learning is happening. So this could be this could get like this could highlight the accuracy of machine learning. So this is kind of important in quantum neural networks. So today I discussed about how quantum neural networks work and uh, its advantages, and we are going to, it's my turn to discuss the disadvantages of quantum neural networks. And first is noise and error rate problems in quantum gates. We are having a NISQ area, so actual quantum computer is not very good for calculating all stuff. And already what I said from the advantages from data re-uploading and other things are achieved from like in imaginary zero noise quantum computer. Uh, and co- and similar to that, constraints on number of quantum qubits and circuits. As in South Korea, we have 127 qubits superconducting quantum computer on IBM Yonsei, and it's limited to 127 qubits if we can think of this. But in currently, like NVIDIA's GPU and other things can handle a billions or billions data at the same time. So uh, this is our current constraint. And last constraint is due to current quantum computing hardware limitation. This is kind of similar, but like if yeah, in current hardware has like if we calculate on the same qubits many time, its temperature goes up and we could lose the sustainability. So unlike to GPUs, like GPU has a thermal disadvantage, although we have a cooling system to achieve this lowering uh, lo- uh, achieve this high error rate. But superconducting qubits has is kind of very sensitive to thermal error, so this could be a limitation. And so we at this point we use QNN to add just only simulating model, and it's limited to practical use of quantum CNS, quantum neural networks, not CNS. And this is my slide. And thank you for listening my introduction to quantum machine learning. Thank you. Are there any questions?
Okay, can you hear me?
Oh yeah, sure.
So I have a question about quantum machine learning. So you said we have to update the parameterized quantum circuit, the PQC, to optimize the loss functions. Like, do you have a general rule of thumb how to like how to architect those parameterized quantum circuits?
Oh, we have just like the method used in machine learning called like Adam optimizing method or coupled optimizing method. We can use this like this. It's just same way as machine learning process these parameters and how quantum circuit use these parameters. Are you asking this kind of optimization techniques?
No, I'm asking about the structure of the parameterized quantum circuits, the PQC or the ansatz.
Oh
Like,
yeah.
for instance, there are lots of different designs for ansatz, like, for instance, hardware efficient ansatz or unitary coupled cluster, single and double excitations for quantum chemistry purposes. So, are there any general rule of thumb how to optimize the parameterized quantum circuits so that it will reflect so it would be optimal for optimizing a certain loss functions or solving certain problems?
Do you mean like making how to make answers like how to be efficient way or just like SU2 symmetrical way? Are you asking this kind of approach to make variational circuits? It's it depends on the situation and it's like data. So we are going to choose from different algorithm and there are lots of names like called quantum train method like and other things like I don't know, but there was so much of these names, and yeah, there are a lot of things to consider. But I didn't explain in this seminar since it's introductory seminar. So if you're asking this, uh, you can see from my reference paper page. So yeah, is it enough my explanation?
Yeah, sure. Thank you.
Hey, I have a question too. I'm not a professional about machine learning, but I heard that you inject noise into the neural network on purpose to prevent overfitting. And I'm just curious if could quantum noise act as a plus factor to prevent overfitting?
Oh yeah, sure. It's currently studied topic that you are talking about. Actually, the quantum noise is much like 불규칙하다가 영어로 뭐지? Unknown quantum noise is like more
Real random?
yeah, more random to like classical data we want to inject and you like what you said in machine learning we have a data and we intently add noise data to improve the learning process and yeah there are much types of methods that using quantum noise to learning. Yeah, it's currently studied.
Okay, thank you.
Okay, I have one more question.
Okay.
It's kind of similar to Seungbin Guan's question. So as Seungbin Guan said, in classical machine learning, we introduces stuff like L2 regularization to prevent overfitting from happening. Like that's basically saying initially adding noises to the loss functions. Are there any similar aspects in quantum machine learning stack? Do you also specifically design the loss functions to match the certain purposes?
Actually, for my experiment, I didn't make the such quantum circuits to utilize quantum noise, but from what I researched, there are lots of approaches doing that. Uh, and personally, I didn't have experience with that.
Okay, thank you.
I have another question. Classical deep learning, one of the hyperparameters is choosing which loss function or like which step function to use. So you can use ReLU or etc. And a recent study that I know of is that you actually fix those functions, use those functions as a parameter that you could change. So you also train what kind of functions to use in that process. So uh, regards to quantum machine learning, I believe these functions in activation functions, yeah, activation function is the word. These activation functions in classical machine learning will be analogous to the structure of the ansatz. So I was wondering if there is any attempts in the research field to like parameterize the structure of the ansatz itself so that we can uh research the field of possible answers more effectively rather than trying out different type of answers by hand.
I didn't understand the question correctly. Can I ask that, like, are you talking about that what types of activation function is crucial for, like, optimizing the circuit?
Oh,
Is it what
that, that
what I
was
think?
that was a hook, and so just to make it brief, my question is that well, there's a lot of different structures of ansatz that you can make, and what I'm wondering is that if there is any approach or attempt to parameterize the formation of the ansatz itself to like um to investigate more various types of ansatz computationally.
Sorry, but I cannot understand your questions.
오케이. 오케이. 그 안세트 구조가 되게 약간 정해져 있고 약간 어떻게 보면 불연속적인 아무튼 블록들을 붙이는 느낌이니까라고 할 수 있는데 그런 것들을 어떠한 연속적인 파라미터화 시켜가지고 걔네를 일종의 인공지능이나 아니면 어티마이제이션 알고리즘을 이용해서 최적화하는 그런 시도도 있었을까요?
안삭지가 불연속적이라는 게 무슨 말인지 잘 모르겠는데, 어, 혹시 다른
음,
사람들 질문 없으시면 나중에 해도 될까요?
네.
Is there other questions regarding this quantum machine learning? I think here's Im Hyung-min has a question.
Yeah, I have a short final question.
I think In Hyung-min asked already questions about what's the difference between VQA and quantum machine learning. And VQA is like VQA has a many various aspects regarding QAOA, VQE, and one part of QA is QUBO, and these kinds of things to minimize all the kind of stuff is called VQA. But specifically, quantum machine learning is using quantum circuits to minimize optimization function, like from extracting data and making parameters circuit and updating that to in like the one purpose is just minimizing loss function in quantum machine learning. This is my answer. And what was your questions? Sorry.
Okay, so speaking of like optimizing functions, like there's a universal approximation theorem that states that basically every function can be represented by the neural networks, classical neural networks. So what are the advantages of using quantum neural networks aside from using classical neural networks?
From previous research, quantum neural network has advances from like we have a small number of iterations. It converges much faster than classical algorithm. But regardless of this, as I discussed earlier, we could think of if the hardware goes big enough to handle a lot of data, it's more efficient regarding its calculation power, and we are currently working on such things.
Okay, so are there any like mathematical theorems like proving like quantum neural networks are much more advantageous compared to classical ones?
I don't have any idea about how mathematically it works. Like how it converges first best, then I think it's because of physically qubits most position technique and calculating all the things at the same time. I think because of that.
Okay, thank you.
Are there any questions?
Okay, if there's no more questions, we'll have a 3-minute break and we'll come back at 7:35.